Welcome. In this video lesson, we're going to take a look at some building blocks for vectors, specifically inner products, length, and orthogonality. It turns out that orthogonality is a very important concept, and essentially for vectors in 2 and 3 dimensions, this basically means that they're perpendicular. But it's better to use the term orthogonal since in higher dimensional systems, the notion of perpendicularity does not make sense because that assumes you can measure a 90-degree angle. But orthogonality is actually a useful concept. When you're doing a regression analysis, you want to do a linear regression or quadratic regression. That's based on orthogonality principles. And some very important things come to play there. And when we say higher dimensions, it doesn't mean that when we're outside of 3D that doesn't apply to the real world. In higher dimensions, we simply mean we have vectors that are longer than 3 components. So if you have 10 component vectors where those 10 components are some 10 measurements on people, then absolutely it makes sense to talk about higher dimensions. That would be a 10-dimensional space. So we'll start off with just a review of the idea of dot product. Sometimes this is also called an inner product in linear algebra. And the dot product between 2 vectors is a scalar value. It's a number that you get when you multiply 2 vectors, one that's on its side like this. So notice that this is a 1 by n vector. It has 1 row with n columns because we see that it goes from u1 to un. This one here goes from v1 to vn, but it has n rows and just 1 column. So when you multiply these two together dimensionally, inner dimensions match, and you get a 1 by 1 result. And the result is taken by multiplying the first component of the first vector with the first component of the second vector, and then all the way up to the last component of the first vector with the last component of the second vector. And you sum those results together. So here's an example where suppose we have 3 products that are sold in quantities of 10, 8, and 5. The respective prices are $5, $10, and $20. Use an inner product to find the total revenue. Well, what I want to do is I want to take 10 times $5, 10 units of product 1 times $5 per product 1, plus 8 times 10 plus 5 times 20, because I want to calculate the total across the board. So I can specify 2 vectors. I can say the first one will just contain the quantities 10, 8, and 5. And the second vector will contain the prices of each of those. And I'm going to omit units because we're just trying to calculate a number here. And so I should end up with total dollars. If I sell 10 units at $5 a pop, 10 units at $5 a pop, plus 8 units at $10 per unit, plus 5 units at $20 per unit. Let's see, I'll get $50 in revenue here, $80 in revenue here, $100 in revenue here, and that amounts to $230 of revenue. So that's an application of where we actually use dot product to solve problems. Now, it's also the case that when we compute the magnitude of a vector, we take the square root of the sum of the squared components. And this is due to Pythagorean theorem, at least in 2 dimensions, where if I have a vector in here and I want to, let's say that's the 1, 2 vector, and I want to figure out its length, I create a right triangle like this. This length here is 1, this length here is 2, this is the vector x. So then I could say that the length of vector x is equal to, by Pythagorean theorem, the length of x squared is equal to 1 squared plus 2 squared. So the magnitude of x is equal to the square root of 1 squared plus 2 squared. So we see that that's just the square root of the sum of the squared components of our vector. And in n dimensions, it's the same principle. So with respect to dot products, how this helps us is because I can express the length of a vector in terms of the dot product. So here we see that this is just the sum of the squared components. Well, if we think about what x1 squared is, that's just x1 times x1, and plus x2 times x2, all the way up to plus xn times xn. Now that's just a dot product that's already in expanded form, just like here, this is already a dot product in expanded form. So if I put this back together as a dot product, I'll have x1, x2, all the way up to xn in my first vector, and x1, x2 all the way to xn in my second vector. And we see that this is really just vector x And it's the transpose of vector x, because if we think about a vector, usually we think about a column, and if you want that to specify that vector being on its side, then the transpose of it turns the column into a row. And dot that with the vector x, and you see that that's basically another way to compute the sum of the squared terms. And then the square root of that is, of course, gives us the magnitude. Another common way of writing out dot products, I don't know if I've mentioned it here yet, but sometimes rather than writing out, yeah, here it is. So this method up here, anyway, allows us to quickly compute the magnitude of a large vector without having to perform all of the manual squares and addition. So we could create vectors in a programming language and dot two vectors together, and it's one operation. It's one vector operation. Now in linear algebra, we write u transpose times v, just like we wrote here, to make sure the dimensions match. That, well, here we're taking a 1 by n times an n by 1. But a lot of times in classes like multivariable calculus, you just sort of omit the transpose, and it's just understood that if you write u dot v, that you're doing the dot product and that one of them is on its side. So it's totally acceptable to write it both ways. I prefer to specify transposes because unless you're specifically using the dot product function in like Python or something, then if you multiply two vectors together that are both, say, 3 by 1, you're going to get an error. But needless to say, if we interpret this as being the dot product, then all is good. So here are some properties of dot products. Dot products can take place either way. So if you think about why letter A is true, we need not go further than this example here. If we just commuted the 10 and the 5 and made this 5 times 10, 10 times 8, and 20 times 5, the 5, 10, 20 could have been in this vector, and the 10, 8, 5 could have been in this vector, and we would have come up with the same answer. So we would just be multiplying the terms or multiplying the factors in reverse order. Distributive property also, you can talk about the distributive property. You can distribute the vector in here. You can see that we're just taking w and just back distributing it into the parentheses to make w times u, and u times w and v times w. But since multiplying dotting two vectors in reverse orders produces the same result, this would be the same thing as saying w dot u plus w dot v. Now notice also that this notation doesn't have the vector marks over it. The vectors are just bolded, so that's also a common convention. But when you write down a vector, you always want to put the vector hat over it to differentiate it from a scalar. You can see here we're using unbolded c to represent a scalar. And here we're just saying that if you scale a vector first and then dot it with something, that's the same answer you would get as if you dotted the two vectors first and then scaled it. So the constant, just like with matrix algebra, can be passed in between vectors and matrices. And u dot u is greater than or equal to 0, and u dot u is equal to 0 if and only if u is equal to the 0 vector. Okay, so if you dot a vector with itself, you're always going to get a positive number, or a non-negative anyway, because if you're multiplying the same component by the same component, you're essentially squaring the components, like here when you do x dot x. So squaring will always take away the signs. And the only way to get the dot product of 0 is if you're dealing with the 0 vector. So you'll see this lesson's kind of more bits and pieces of concepts. So here, let's say that you and your friend are at two different locations in two-dimensional space, and we want to know what's the distance between you and your friend, then find a general formula to express the distance between any two vectors, x and y. So here is a representation of our 1, 3 vector. So 1, 1, 2, 3. There's the 1, 3 vector. There is x. And then y is the vector 2, negative 1. So 2 and then negative 1 unit down here. And we want to know how far apart are these two vectors. So in order to be able to do that, we need to think about the distance between them as the distance between the two tips right here. And because this location right here is 1, 3, and this location here is 2, negative 1, we really can still form a right triangle out of this. And the way we could do that is by thinking about it like this. We could say, well, this is really a right triangle that looks kind of like so, where this unit right here is the difference between the x values. So the x value goes from a 1 to a 2, so this would have to be a length of 1. And then the drop goes from 3 to -1 in the y direction. That's a drop of 4 units. And now we could use Pythagorean theorem to do that. So another way to think about this, though, is that if we connect 3 vectors together, they're now established as being tip to tail. So if I think about this red vector here as, we'll give it another name, we'll call it z for the moment, then what's the relationship between x, y, and z? Well, they're all kind of tip to tail. Where z points, we'll just say z has its tip down here. You could draw it the other way as well, it wouldn't make a difference. But in this case, we could say that x plus z equals y, because we're doing tip to tail. X plus z equals y. And so that means I could re-express z in terms of x and y. I could say z is equal to y minus x. Now, since I want the length of z, that's equivalent to saying length of y minus x. So the length of y minus x is simply going to be, so that's the length of z by the equality is equal to the length of y minus x. And the length of y minus x is simply the length of the difference between the two vectors. So if that's going to be the difference between 2, -1 minus 1, 3, then you're going to see that the vector that we're actually measuring the length of is the vector 1, -4. And that's exactly what we have here, 1, -4. So to compute the length of that, that's just going to be the square root of 1 squared plus -4 squared. So in order to find that, we just have to subtract the two vectors and find their length that way. Another way you might see it written as in general, you might see something like this. Or x, you could say if these components are called y and these components are called x, you could say y1 minus x1 squared plus y2 minus x2 squared, and so on, because we're taking the difference between them. So there's kind of our generalization of that formula.